This is a lecture for Chapter 8 for Stats 253 on p-values. The idea of a p-value is very, very simple, and it's used, p-values are used universally. They're always included in results in journal articles that are published. Okay, so what is the p-value? Well, think of the hypothesis testing that we discussed so far. For the hypothesis testing, we said first you have some distribution which you know, and you choose a confidence level. So you choose an alpha. From that alpha, you find the tails so that the area under the tail or tails is equal to alpha. You find the critical value, which is a value of z or t right at the edge of the tails. Then you compare your test value to that critical value and determine whether the test value lies in the non-critical region, in which case you're going to not reject the null hypothesis, or it lies in the critical region, in which case you will reject the null hypothesis. So a lot of work went into that, and also a decision was made at the onset by the person doing the calculation as to what confidence level was acceptable. Is it 90%, 95%, 99%, or some other level? You made that decision. Now, p-values just sort of wipes all that away and lets the decision about whether it's a critical region or not, doesn't even really come into it, but it lets the person who's reading the journal article decide for themselves whether the result is significantly different from the previously held value or not. So what is the p-value? Okay, remember the critical value is a value of z or a value of t. The p-value is not that, it is the area. It is the area to the right or to the left of the test value, or sometimes you have to multiply by 2 if you have a two-tailed test. Let's look at a normal distribution and I'll show you what I mean. So here's a graph and a situation from a previous video and from the lectures also for the normal distribution. And in this case, it's a left-tailed test, and the error, the alpha, has been set equal to 0.10. That's by a previous decision that 90% confidence was good enough. Okay, using that, this area was found here, so that this area in green, the total area of that is 0.10, and then the critical value of minus 1.28 is found, and that's a value of z right here at the edge of the critical region. And here's the test value coming in at minus 1.67. Okay, what is the p-value? The p-value, get a contrasting color here, the p-value is the area beyond, I'll say beyond in this case to the left, of the test value. But what's that area? This whole area was 0.1. This is probably, so your p-value here, remember p-value is an area, critical value is a value of z. So they're both using the word value, but they're very different. Okay, say this area is 0.07. So the p-value associated with this test and this situation here, because you're using the bill-shaped curve off the original data, so this p-value is 0.07, and it would be published along with this result. And someone could look at it and say a p-value of 0.07, well, that's pretty small compared to 0.1, which I typically use, so yeah, I'd say that that'd be a case for rejecting the null hypothesis. So that's what we're talking about. The p-value is the area beyond the test value. If the test value was up here, the p-value would be this area under the right tail. If the two-tailed test, you have to multiply that area by 2 to get the p-value. So now that you saw a killer word here, it is in words. So the p-value is a probability that the test value or a more extreme value would have occurred. That's what it says. And that's that area beyond the test value. So in terms of the hypothesis testing, what you're saying with the p-value as a probability is that if you're assuming that the null hypothesis is correct, is valid, then the probability that that test value would have occurred, or a more extreme value would have occurred, is the p-value. Remember, the areas under curves are probabilities. If it's a right-tailed test, of course, it's the area to the right of the test value. If it's a left-tailed test, it's the area to the left. For a two-tailed test, you find one area and you multiply it by 2. So then now you can make a decision to reject or not reject the null hypothesis by using the p-value and your own chosen confidence level. Right, so you don't have to compute the critical region or the critical value at all. So let's look at how decisions are typically made with these p-values. Okay, let's say you get a p-value of less than 0.01. Well, that's pretty small. In this case, it's usually assumed that the null hypothesis should be rejected. This would correspond to a confidence of 99% or greater. Remember, p-value is smaller, then the confidence is going to be greater. Okay, so this is a 99% or greater confidence of not making a type 1 error in rejecting the null hypothesis. If p lies between 0.05 and 0.01, this sort of corresponds to the region of 95 to 99% chance of not making a type 1 error, and usually the null hypothesis is also rejected. So what happens if p is between 0.01 and 0.05? Then you have to think about the consequences of rejecting a valid null hypothesis. And this was one of the questions in the homework on the case of the drugs, which is a worse error to make, type 1 or type 2, and that depends on the circumstance. Okay, for example, if you have a drug that's not effective and without it many people die, well, then that's pretty high, that's a pretty extreme consequence. But if you have a drug that's maybe, okay, not so effective, and you use it and it really doesn't do anything, but it has side effects that are horrible, then that's a worse error. So you have to consider the circumstances and the consequences of rejecting the valid null hypothesis. So this is sort of the gray area here between 0.1 and a p-value of 0.05. Now if the p-value is greater than, whoops, that should say, I'm sorry, that should say the p-value is greater than or equal to 0.10. So exactly at 0.10 corresponds to 90% confidence level. But now you're even greater in your alpha, means 90% or less confidence. In that case, the null hypothesis is usually not accepted. And like I wrote here, p-values for a study, that's for some statistical study, are often published or required when publishing in a journal article. Then people can look at the results and consider whether it belongs to this, or this, or perhaps this case. Whereas if you did the whole hypothesis testing and just said the null hypothesis is rejected with a confidence of 95%, a person doesn't have quite the handle on the data as they do when you give them the p-value. Now, how do you use R to find the p-value? Well, we're looking at the normal distribution and the t-distribution. For the normal distribution, you don't necessarily have to go to z-values, but let's just go to z-values anyway. So the z-value is going to be the, I'll say theta nu minus theta naught over the sigma over the square root of n being the sample size, sigma being the standard deviation of the original data. Okay, so now you have a value of z. Right, this is your test value. Right. You want the area beyond the test value, and the area under the curve is given by p norm. It's that probability, and so to get the p-value, you would want to find the probability let's say you had a left tail test. You would give the value z here, and you're done. And what's returned here would be the p-value for a left tail test. If you have a right tail test, give the z value, and then set lower dot tail equal to false. You'll notice in the R tutorial that I don't just give z or z test, I do absolute value of z. Oops, I'm sorry. Absolute value of z. The reason for that is, well, consider that I did something wrong in my calculation, ended up with a negative sign. Okay, so let's say z, and I should have put test, but let's just say z is 1.5. Okay, here's my 1.5 here. If I say lower tail equals false, I'll get this area up here. If I don't, and I leave lower tail equals false off, then I'm going to get, whoops, then I'm going to get this area down here. You see, that will be not exactly a tail. Okay, and the same thing happens if you have a negative value. Say your z comes in at a negative value, say negative 1.6. If lower dot tail is equal to true, set equal to true, which is the default value, then you get this area here. But if you set lower dot tail equal to false with a negative value, you're going to get all this area out here, which is sort of unphysical, and that's not what you wanted in the first place. Okay, so that's how to use a normal distribution to get the p-values, and the situation is very similar for the t-distribution. Again, this is all in the R tutorial, but you find your t-value for the test. So here was your test value, your new value minus the old value, and now you're going to use the standard deviation from the sample dividing by the square root of n. Remember, you're going to put a lot of parentheses in here to make sure things come out right. Okay, to find the p-value, you use pt, give it t, this t from up here. I might give it a little better name than that. Then you have to supply the degrees of freedom, which is n minus 1, and then you have the option of lower tail equal false or lower tail equals true, which is the default value. So basically that's the same, and like I said, it's also covered in the R tutorial.